Hello everybody, and welcome back to another video. In this video, I'm working on a blackboard, and I have a face reveal. So, the question today is, how fast must we launch Scrat, which is the squirrel from the Ice Age, such that he will never touch down back on Earth? So he's going for the acorn, he's running up to it, and then boom, some lever or explosion launches him right up into the air, and he has just enough energy that he never comes back down to Earth. So what we are saying is that he is launched off of Earth, so he has an initial distance of r0 away, which is the radius of the Earth, and he is launched so far, in fact, infinitely far, such that when he has been traveling forever, so the limit as time approaches infinity is, and results in his energy at this point being 0 joules. So he has a velocity of 0 right here. He's not moving anymore, but he's infinitely far away. So there's no force of gravity pulling him towards the center. So he just stays there forever. This is hypothetical, because he would never reach this point. He'd just keep on going slower and slower and slower forever. Now, in order to get started, we are going to look at how much energy he has initially, which, since there are no net forces on this system, must also be equal to how much energy he has at the end. So we have I is equal to EF, and work is equal to 0 joules. So these two statements are saying the same thing. So there's no net force on the system, is essentially what that is saying. So now we will begin by writing out our initial energy. So E1 is equal to our kinetic energy, 1/2 mv squared, plus our potential energy with respect to infinity. So what we will do, since this is a large radius, is we will look at this graph of Fg versus R, and since Fg is proportional to 1/r squared, our graph will look something like this. So our area under this graph is equal to force times displacement in the direction of the force, since we are pointing in the same direction for both of these, which is equal to, this is a dot product, and these are both vectors, but you don't need to know that right now since they're in the same direction. This is equal to our work, or not really work in this case scenario, just kind of our energy. So, starting from our radius of Earth, we have, and then going to another radius, which is, let's say, is R1, we will gain the area under this equivalent in energy. However, this is not a universal case scenario. So what we do in physics is we integrate this to infinity. And you were using this as our reference frame. So what we have is our constant times the integral from infinity to our radius. So since this is from far away point to close point, and this is all positive, our answer is actually going to be negative, because it is relative to right here. Since if you are really far away from an object, infinitely far in this case, you have all this force pulling you this way. It's very low at first, but it grows and it grows and it grows and it keeps on growing until you get to the initial radius. Then you have a velocity which is proportional to the energy gained in this. So it is the integral from infinity to the radius of the Earth of this constant times 1/r squared dr, which is equal to, in this case scenario, g times the mass of the object, which is a squirrel, by the way. This is mass of object, times the mass of the planet. This is all of our constants, negative divided by r. So this is our answer right here for how much energy we have at the initial point. We have 1/2 mv squared plus negative g m of the object, mass of the planet, divided by the radius of the Earth. So this is our initial energy, which now we know, and we also know E1 equals EF, and the final energy is equal to 0, so that means that 1/2 mv squared minus g, this is mo, g mo mp over r is equal to 0. So adding this to both sides, and we get 1/2 mo v escape squared is equal to g times the mass of the object times the mass of the Earth divided by the radius of Earth. So you can multiply both sides by 2 and then divide both sides by the mass of the object. So this cancels, this cancels, this cancels, this cancels, this cancels, this cancels, and we get v squared is equal to 2g times the mass of the Earth divided by the radius of the Earth. So we can write v escape is equal to g 2g m of the Earth divided by the radius of the Earth. Now, when we plug all these in, since this is our velocity, we get 2 times 6.67 times 10 to the negative 11 newtons times kilograms squared per meters squared times 5.97 times 10 to the 24 kilograms, which is the approximate weight of Earth, divided by the radius of Earth, which is 6.37 times 10 to the 6th meters. And this will give us an answer in meters per second. And when you plug this all into a calculator, you get about 11,100 meters per second. So this is in meters per second. This is our answer. Now, you can't really think about that too well if you're here from America like me. So another way of thinking of this is every second you move 417 miles. This is so fast. Think about that. 60 miles an hour in a car seems like you're just zooming. You are going 417 miles in 1 second. You could scale the continental United States in minutes. It'll take you about 20 minutes to get from the South Pole to the North Pole, assuming you went straight through the Earth. That is crazy fast. So this is our answer. This is our main answer, since most people use metric system, especially while working in physics. However, I just thought this was a really cool visualization. I want to thank you for watching, and let me know in the comments if you like this new style of video on the blackboard. Thanks for watching. Please like and subscribe if you enjoyed, and I'll see you in the next one.